Hello everyone! Today we're going to dive into one of the most fundamental and high-scoring chapters in your Class 12 chemistry syllabus, solutions. I know chemistry can feel abstract with all its formulas and theories. But the chapter on solutions is different. It's all around us every single day. The air we breathe, the sweet tea we drink, solutions are part of our daily experience. Understanding this chapter is more than passing an exam. It's understanding the world on a molecular level. It often appears in board exams and competitive tests, so get a strong grip now. It will pay off. Let's think about why this chapter matters for exams. Examiners love how it connects physical concepts and chemical principles. You apply mathematical formulas to real-world chemical scenarios. That tests calculation skills and conceptual understanding. Questions are often predictable and based on core ideas. With focused effort, you can master this chapter and confidently tackle any question. We'll break down every concept step by step. So what exactly is a solution? In the simplest terms, a solution is a homogeneous mixture of two or more substances. The word homogeneous is key here. If you take a sample from the top of the mixture and another from the bottom, their composition will be exactly the same. Think about dissolving salt in water. Once you stir it well, you can't see the individual salt particles anymore. In any solution, we have two main components, the solute and the solvent. In our saltwater example, salt is the solute and water is the solvent. We study solutions because they are the medium for the vast majority of chemical reactions. Life itself happens in a solution. Our blood is a complex aqueous solution that transports oxygen, nutrients, and waste products throughout our body. Many industrial processes rely heavily on the principles of solutions, manufacturing medicines, producing beverages. When we think of solutions, we often picture a solid dissolving in a liquid, like sugar in water. But solutions can exist in all three states of matter: solid, liquid, gas. The air we breathe is a perfect example. It's a solution of nitrogen, oxygen, argon, and other gases. Even more interesting are solid solutions. Metal alloys are the best example of this. Brass, for instance, is a solid solution where zinc, the solute, is dissolved in copper, the solvent. Once we have a solution, a very important question arises. How much solute is actually in it? Is it a little or a lot? Chemists use the term concentration to describe this. A solution with a small amount of solute is called dilute, while one with a large amount is called concentrated. But a little and a lot are not very precise. To be accurate, we need specific quantitative methods to express concentration. One of the most common ways to express concentration is molarity, represented by a capital M. Molarity is defined as the number of moles of solute dissolved in 1 liter of the solution. A mole is just a specific number of particles, kind of like how a dozen means 12, and a liter is a measure of volume. So, a 1 m solution of sodium chloride or NaCl means you have 1 mole of NaCl particles dissolved in enough water to make exactly 1 liter of the final solution. Another important concentration term is molality, represented by a lowercase m. Molality is defined as the number of moles of solute per kilogram of the solvent. Notice, it's about the mass of the solvent, not the total volume of the solution. Why do we need this separate measure? Because volume can change with temperature, but mass does not. Besides molarity and molality, there are other useful terms like mole fraction and normality. For your exams, focusing on mastering molarity, and mole fraction is the most important step. Have you ever noticed that you can keep adding salt to water, and it will keep dissolving but only up to a certain point? After that, no matter how much you stir, the extra salt just settles at the bottom. This limit is called solubility. Solubility is defined as the maximum amount of a solute that can be dissolved in a given amount of solvent at a specific temperature. A fundamental principle that governs solubility is like dissolves like. This simple phrase is a powerful guide. It means that polar solutes tend to dissolve in polar solvents: salt, sugar, water. On the other hand, nonpolar solutes dissolve in nonpolar solvents: oil, grease, gasoline. This is why water can't wash away an oily stain from your clothes, but a special nonpolar solvent in dry cleaning fluid can. Temperature plays a major role in solubility, but its effect depends on the state of the solute. For most solid solutes, solubility increases as the temperature increases. This is why you can dissolve more sugar in hot tea than in iced tea. For gaseous solutes, the opposite is true. The solubility of a gas in a liquid decreases as the temperature increases. A warm soda goes flat faster than a cold one. Dissolved carbon dioxide escapes more easily from warm liquid. For gaseous solutes, pressure is incredibly important. Henry's law. Gas solubility in a liquid is directly proportional to the gas pressure above the liquid. Think about a sealed bottle of soda. It is bottled under high pressure, forcing lots of carbon dioxide into the liquid. The moment you open the bottle, you hear that psst sound. The pressure above the liquid drops, the solubility of CO2 decreases, and the gas starts bubbling out of the solution. Now we get to one of the most interesting parts of this chapter: colligative properties. These are properties of solutions that depend only on the number of solute particles dissolved in the solvent. They do not depend on the identity or nature of those solute particles. It doesn't matter if you dissolve sugar or salt. What matters is how many particles you add. There are 4 main colligative properties we will look at: boiling point elevation, freezing point depression vapor pressure, lowering osmotic pressure. The first 2 are related to phase changes: boiling point elevation and freezing point depression. Adding salt to water when cooking pasta makes the water boil at a slightly higher temperature. This is why salt is used to de-ice roads. The salt and water solution has a freezing point below 0 degrees Celsius, melting the ice. The third colligative property is the lowering of vapor pressure. Solute particles at the surface block solvent molecules from escaping into the gas phase. Finally, we have osmotic pressure. Osmosis is the spontaneous movement of solvent through a semi-permeable membrane from lower solute concentration to higher solute concentration. This is vital in biology. Plant roots absorb water from soil through osmosis. Kidneys regulate body water balance via osmotic processes: boiling point elevation, freezing point depression, vapor pressure lowering, osmotic pressure. These 4 properties are powerful tools for determining the molar mass of unknown solutes. Understanding these concepts gives you the foundation to master solutions and excel in your chemistry studies.